Hi there. So today we're going to have a look at the nature of quadratic roots. So let's have a look at our infamous quadratic formula, our minus b formula. So you have minus b plus or minus the square root of b squared minus 4ac all over 2a. And where is these a's, b's and c's coming from? Well, they're coming from a generic quadratic of the form ax squared plus bx plus c, where a is the coefficient of the highest power, in this case the squared, b is the coefficient of the lowest power of the variable, in this case the single variable x, and c will always be the constant. So this is how you would fill it out. Now there's a built-in minus there, and there's two versions, a plus and minus versions. You always have to take that into account, which is why I always use brackets. However, if you look at this very carefully, when you're putting in your numbers here, the only thing that's actually important in this whole sum is what's happening underneath this underneath this square root in here. That's the only important bit. The rest you're just adding and subtracting a number and dividing by a number. Adding and subtracting and multiplying and dividing, they don't really do that much. It's here. This is the actual thing that matters. And we call that, it does actually have a name. It's called a discriminant. Okay, and the reason it's called a discriminant because it discriminates. It's a discriminator, and sometimes discriminators get a bad rap, but this one is a good discriminator because what it discriminates is it discriminates real roots from complex roots. And some people, me included, sometimes I call these complex roots imaginary roots. Okay, a lot of mathematicians will sniff at you if you say imaginary because, they can't be imaginary because no such thing as imaginary. But listen, that's a philosophical debate, but complex roots, in other words, roots that can't be written normally in terms of a rational number or in terms of a square root of a positive number. So that's what we're going to use them today. So I'm going to show you what I mean by that. Let's say you find the a, b, and c from a particular quadratic and you pop them into the discriminant. If that answer is greater than 0, then this is the way your graph is going to look like. Okay, so let's just draw a generic quadratic graph. You will get two distinct real roots. So the numbers will be real and they won't be the same number. Similarly, if I pop numbers in and they're equal to 0, I'll also get real roots, but the two numbers will be the same. Okay, they'll be actually the same number. So it'll be a quadratic, but when it solves, it'll solve for the same number. Usually the difference 2 squares, something like that. Okay, and the third type then, and this is where the discrimination occurs. If it's less than 0, well then you will get a quadratic where you have no real roots. They won't touch the x-axis. So the answers you get will be either an error on the calculator or you'll have to use complex number formulations to generate them. But this little is a test, it's a little litmus test, just a test. Greater than 0, 2 real distinct roots. Equal to 0, 2 roots that are exactly the same, but they're also real, and less than 0, not real roots, in other words, complex roots. So let's do a couple of questions just to show you how this can kind of work. And there's lots of different ways this can be presented in the test, but I'm going to give you a couple of examples, okay? I'm going to show that k minus 2 x squared plus 2x minus k equal to 0 has real roots. Okay, so how am I going to show that that has real roots? Well, if it has real roots, it must be either b squared minus 4ac greater than 0 or b squared minus 4ac equal to 0. So the easiest way to work this one out is prove that b squared minus 4ac is greater than or equal to 0. That would prove that it has real roots. So there's your kind of discrimination. It could be real and distinct, it could be real and equal, but it's just real. That's your basic operation for real. So let's write down our a, b, and c. A is always a number in front of the x squared. In this case, k minus 2, that's a number. B is always the number in front of the single variable. In this case, B is 2. And c is always the constant. In this case, c is minus k. So we're going to pop them in and see what happens. B squared. So, sorry. B squared. We use brackets to protect everything. Minus 4 times a by c greater than or equal to 0. So let's have a look at this. 2 squared is 4. Minus k, minus 4k by minus k is plus 4k squared. And minus 4 times minus 2 is plus 8 times minus k is minus 8k. Now I'm going to rearrange this to make it look like a quadratic. Now, there has to be a way of simplifying this. You could divide everything by k or by 4, or you could recognize that that is just so you could divide everything there by k and you get k squared minus 2k plus 1, which would be the difference of 2 squared, k minus 1 to be squared, or in this case it's 2k minus 2 to be squared, the same thing. But this is true for all k an element of the real numbers. Why? Because no matter what number I put in there, so long as it's a real number, okay? So long as it's a real number, it's going to generate a positive number or a 0. And if it's a positive number, it's going to be greater than 0. And if it's 0, it's going to be equal to 0. So it fills both criteria. So that's how it makes that true. Okay? I'll show you another one. Right. So let's have a look at one. M plus 3 x squared plus 6 minus 2m x plus m minus 1 equal to 0 has equal roots. So let's show that. If it's equal roots, then b squared minus 4ac is equal to 0. Let's have a look at that. Now, there's a caveat on this. It has equal roots if m is equal to 3 over 2. So let's pop everything in here. What's a? A is the number in front of the x squared, in this case m plus 3. B is the number in front of the x, in this case 6 minus 2m. And c is the constant, in this case m minus 1. So I'm going to pop everything in. 6 minus 2m squared minus 4 times m plus 3 by m minus 1 equal to 0. So let's see, can I work this out? Let's do our algorithm on this. Square the left, square the right, multiply them together and double it. And then, listen, we could do it in one go, but I'm not going to be brave. I'm going to multiply this out. M times m squared, 3 times minus 1 minus 3, and a 3m and a minus m is a 2m. And then I'm just going to multiply that out and tidy it up. 36 minus 24m plus 4m squared minus 4m squared minus 8m plus 12 equals 0. So I can see that they automatically cancel, and I've got 36 plus 12 is 48, and I have minus 32m, and that would mean equal to 0. Minus 32m is equal to minus 48. Divide both sides by 48. M is equal to 3 over 2. QED. There's your proof. Okay, it's true for that when M is that. Okay, and that's how you use this to test. And it is quite handy to use to test. So for those 3 distinct properties of roots.